Pop, 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 pop. All right, I'm now recording. All right, it's official, gamers. All right, and then with regards to the, so this is on the 10th. Yes. So with regards to the formula sheet, we're not going to do one today. I'm going to do one completely and then send it to you guys tomorrow or whatever, because I have another study session scheduled for today immediately after this one for Kelsey. So I have to go and do that as well, because that final's on the 8th, so that's closer. All right.
Kelsey, those were the days.
Yeah, easy peasy. All right, so we can start with just running over these questions. So a lot of these things are just like when it comes to true, false, and multiple choice, they're almost all like just recognition, like just remembering it. And it either comes from this PowerPoint, his characteristics for the Mosfet, and then for the PN junction, it comes from applications of PN junction, and then the PN junction IV and equilibrium. And then I think this one is under bias. So these three for PN junction have all multiple choice answers distributed amongst them for the most part. And then for MOSFET, it's really just this one and this one, these two PowerPoints. You can even see the exact same figure.
Like which number?
This PowerPoint is 20, lecture 20 and 21 for MOSFETs. And then PN junction, this is the equilibrium. It goes 11, 13, and 14, because 12 was the midterm, I think, or a quiz review slide. One or the other wasn't important. And then this is like the intro PN junction. No, this is equilibrium. Yeah, 9, 10, 9, 11, 13, and 14. All right. This is the final exam lecture. Did I download this? Yes, I did. So I can get rid of this. All right. So we can start going through these. And then when we get to the problems, actually, we're just going to take the quiz again. All right. So question 1, what is the magnitude of electric field in a PN junction diode, or the magnitude of an electric field in a PN junction diode is minimum under equilibrium? The magnitude of the electric field in a PN junction is minimum under equilibrium. Well, the maximum electric field in a PN junction occurs when it's in reverse bias. So the questions did change. This is not a, they do change. That's awesome. All right, well, that's cool. All right, the magnitude of the electric field in a, so the max electric field that a PN junction diode can experience is when it's under reverse bias. That's when it's dissipating the most energy because very little current's coming through. So what's happening then, the magnitude of the electric field in a PN junction diode is minimum under equilibrium. If there's no applied voltage, the magnitude of the electric field is small. But then if there's an applied voltage across it in the forward bias direction, it should cause the electric field to go smaller. So I don't think equilibrium is at its minimum. I think it's at a center point because its maximum is during reverse bias. Therefore, its minimum should be during forward bias.
Yeah, that's what I remember too.
Yeah, so we would say false here because it's not under forward bias. It's under equilibrium, which is the intermediate state. All right, a PN junction diode or a PN junction is forward biased if higher voltage is applied to the N side with respect to the P side. So this is an electrostatics thing. So when you think of a PN junction, you have your P, which is doped with acceptor, therefore positive ions. And then you have your N, which is doped with donor, which is negative ions. So you have a plus minus, looking from left to right, PN, plus minus. If you apply a higher voltage to the N side with respect to the P side, that means the potential across the system is plus or minus plus. So you have a set of applied voltages going this way and the PN junction voltage going this way. They're going in opposite directions. So what this causes is your, here, I'll show you this little doodle of it. Can you even see that? Yes, there you go. So you see that the signs are paired. They're not repelling each other, they're attracting each other. So the signs or the charges of the PN junction, which are the smaller ones that are closer together in the center, are pulled away from each other by the applied voltage. When they're pulled away from each other, the depletion region increases in width, or at least is, just increases in width. So what happens is it's not forward biased. This is the definition of reverse bias. This is when, the resistivity jumps up, the electric field hits max, because you're putting the voltage potential in the wrong direction and pulling the things away from each other. If it were the opposite way, then it would be forward biased. But in this instance, it is reverse biased. So there's a lot of ways to explain it, but I found it helpful to think of it as just, electrostatics problems. You put an electron and a electron and a proton next to each other, they're going to connect. So it's just going to pull them away from each other as opposed to pushing them together. And then right here, so this is a question that if you've ever plugged an LED in before, you'll know the answer to. An LED will produce more light when forward biased. So we're aware that an LED is a PN junction, and we also know that if you plug an LED in the wrong way, it doesn't generate any light. When it's plugged in the wrong way, it's reverse biased. Therefore, it will produce more light when forward biased. That's correct, because it produces very little, if not zero light at reverse bias. The on current direction in a MOSFET is into the drain for NMOS and out of the drain for PMOS. So this is true. This is just something to remember. It's into N, out P. I just remember in N, and then the other one's just the opposite.
Yep, that's what I do too. It's super handy.
Yeah, because when it comes to these questions, as I said earlier, there's no calculation to be done for a single one of them. It's all just remembering topics or concepts. This is something he did in his second to last lecture, where he just talked about applications. A floating gate MOSFET is used as non-volatile memory. Yep, that's true. Question 6, a good diode offers high resistance in the forward bias. No, it doesn't. That's not what you want to happen. That's the reverse of what happens.
Yep.
So that's just another quick one. Source and drain of the P-channel MOSFET is made of highly doped acceptor region. This is true. You just look at the structure, the 3D structure of the MOSFETs, and you'll see. So this isn't telling you. So here's the description of them. So if we look at it, let's look at a PMOS here. PMOS, P-channel. Look, we have N-channel substrate, but the source and drain are composed of P, or acceptor. So this is all about the structure of the separate devices here. So if it was asking about the NMOS and asking about the source and drain composition, it would be donor, you see, N-type. And then the channel region is the inverse of the actual thing. So channel region here is P when it's an NMOS, and the channel region is N when it's a PMOS. But the source and drain here is the same as its namesake. So that's true. Wait, no, fuck, I already answered that. All right, yes, true. And then over here, on current of a MOSFET increases with longer channel length. Well, when a channel is longer, it has a higher resistance. If you think of Ohm's law, V equals IR, and rearrange it to solve for current, you just have V over R is equal to I. The longer the channel length, the higher the resistance, the lower the current at a standard constant voltage. Therefore, that this is on current increase, it's false, it decreases. That's just an Ohm's law thing, because the longer the channel length, even if it's a low resistivity material, it still increases the resistance more than if it were shorter. Then we have question 9, resistivity of the depletion region is independent of applied voltage. So this is false, it is not independent, and there's an equation for this. So, was it up here? It might be in here. So there's an equation that directly relates the applied voltage to diode resistivity. And we might just need to use a homework for that. Let's see. If we look for one that's asking for resistivity, it's going to be this one then. And this will obviously be something you'll throw on your equation sheet. Right here. So this is talking about the resistivity here. And this is the junction law and everything, a rearrangement of that. So the standard junction law, look, VA is composed for the resistivity because VA will affect your doping densities. Therefore, VA has a direct relationship to max resistivity because resistivity is dependent on the doping densities, both N and P. Therefore, the law of the junction, which takes into account applied voltage, directly cascades down and is applied to resistivity. So another thing about these questions is if you have your formula sheet, a lot of the questions are just essentially you can answer them correctly by just looking at a formula and understanding what it's saying or how it's used later on. So the resistivity is independent of applied voltage. It is not, as we saw in that formula, VA is in the formula. Therefore, it's not independent. This is another memorization thing. Source of inversion carriers in a MOS capacitor's doping density. It is not the source of inversion carriers in a MOS capacitor's thermal generation. If you just need to remember that. In the last quiz that we took, that was a multiple choice question as opposed to a true false, but it was still there. So it showed up twice so far. It might show up again. There's a pretty good likelihood it'll show up again. Question 11, the threshold voltage of a MOSFET device depends on the following. This is something you literally look at the equation for threshold voltage. And since whenever you do a question, whenever you do like a problem that's about the MOSFET, you're always given this, this, and this. And that's because the first thing you're asked almost every single time is what the threshold voltage is. And all three of these things factor into the threshold voltage equation, which should be right. Where are you hiding from me?
Probably not.
Yeah, threshold voltage is right here, which is dependent on these separate equations, which all of them, as you can see, we have one, there's oxide. What are the other things it was asking about? It was asking about oxide thickness, the doping, and the dielectric constant. And if we look right here, threshold voltage is composed of these parameters. In this instance, this and this. You can look here, we have doping density, there's one, and then primarily in Vox, we have both the oxide thickness and the oxide dielectric constant. So it's dependent on all of these. So it's all options are correct. Question 12, when minority carriers pile up at the oxide silicon interface of a MOS capacitor, what is the bias condition? So this is another memorization. So there's two types of piling up, but when that piling up occurs at the oxide silicon interface, it's inversion as opposed to accumulation. So when it's all about this. When it occurs at the silicon oxide interface, it's the inversion. And then question 13 is, how does temperature affect the threshold voltage? It decreases. With an increase in temperature, the magnitude decreases. So I think I could explain this with Ohm's law as well. Let me think about this. V equals IR. Up. We know from this class that when you increase the temperature of a doped or intrinsic, whatever, if you increase the temperature of a semiconductor, there's a point at which primarily, let's say in a doped and not an intrinsic semiconductor, you generate more carriers as opposed to a metal, which is when you increase its temperature, its resistivity goes up. There's a point in time where when you increase the temperature of a semiconductor, its resistivity goes down. And because its resistivity goes down, the voltage increases, right? And you'd think that, and if you thought that, then you would answer incorrectly here. But the magnitude of voltage decreases here, the threshold voltage, because there are other things that are affected because of the equations that threshold voltage depends on. This is a slide. No. Yeah, it's right here. So we have two things. This and this. It was in a slide somewhere, and I forget the actual reason. We'll go back for that in a second, because we're going to actually work through these problems. This is more important, because this is 70 points versus 30. When it comes to this, you could either know it through and through, or you can just remember. And then question 14, when voltage drop is 0 in the oxide for a MOS capacitor, what is the bias condition? Well, across, yeah, it's here, it's going to be flat band, which is essentially, just equilibrium to a point. So what happens is when in any type of system where you're putting any type of potential across a MOS capacitor, voltage drop is always highest in the oxide. So if there's no voltage drop in the oxide at all, there's no voltage drop anywhere else. Therefore, it's at flat band or equilibrium. And then, which of the following conditions of the MOSFET channel describe correctly the on and off state? So when current is flowing, we're at inversion. So that's on. Nowhere else does it say inversion is the on state. Therefore, this is immediately correct. But when it's in the off state, the channel is depleted as well. Wow. And then these are other, obviously these are all wrong. They all have their own places. And then the space charge in the depletion region of a PN junction is due to, so this is the space charge in a PN junction. So this is the equilibrium. We talked about this earlier, those plus and minuses. So when you're looking at a PN junction, he has it in a slide, there's a pretty good one. This one. Right here. Here's your space charge. So this is the whole reason the depletion region even exists. This is what this question's asking about. It's asking about this space charge region, right? So you can see here, the neutral P region is doped with acceptor, and then the neutral N region is doped with donor. And because of the electrostatics, this guy, or P junction, who's doped with donor, and this one who's doped with acceptor, donor, they recombine in the center and they repel each other and they pull away, causing that whole depletion region. And because it's depleted, it leaves behind the opposite of what you would expect, right? Because if you were to answer this question with no, prior knowledge or anything, you would say, or a little bit of prior knowledge, you would say, well, P is positive because it has the acceptor, which is positive, and then N is negative because it has donors. But that's not correct here because it's actually the opposite, because they flip and cause the depletion region. So here you would have negative ions in the P and positive ions in the N, which is right here. Negative on P, positive on N. Question 17. Which of the following diode parameters decides the color for a light emitting diode? It is the band gap of the diode material. So this is material science stuff, but also just something we talked about. I think this is something that we probably talked about in like the applications one, if I had to take a guess, but maybe somewhere else. And then question 18, which of the following conditions increases the electron hole recombination of a p-n junction diode? So this is something that's actually a bit interesting. So when it comes to the phrasing of this question, you can immediately eliminate an answer. This isn't something you actually need to know because the answer here is going to be forward bias. In reverse bias, there's very little current flow. So there's very little going on inside the p-n junction. At equilibrium, there's also no current flow. So what ends up happening is in forward bias, since there's current flow, it's the most likely time when all these electrons are moving across the system, recombining and moving, and that's how they move. They just go through a cycle of recombination and generation over and over again to just move across the system. Forward bias is going to have the highest or increase the electron hole recombination. But the thing is, there are only 3 conditions here and 1 intrinsic thing. Mobility is not something that changes, it's a given. Everything else is a condition. So you can immediately, like when it comes to the phrasing of questions, it's another way you can take tests with very little information. Phrasing of questions can give away the answer like half the time. And this is a good example of that because high carrier mobility is not a condition. Therefore, it can't be an answer. But it's tricky because people might think, because carrier mobility does, contribute to this, but it's not something that changes. It's not a condition. It's an intrinsic state that is given with the problem. It's a constant within a problem. So in this instance, it's forward bias. And then which of the following conditions for an N-channel Mosfet? So this comes straight out of, is this characteristics? I think it comes out of this one, this characteristics. So in this one, it's a memorization problem. So last time I got it wrong and I went back to the PowerPoint to look. And the way you can remember for gate controlled, so there's 2 variations of this. I think it's gate controlled current source, and then it's another controlled voltage source system. So when it's a controlled current source, the two inequality symbols you're looking for are greater than. So let's see if I can find it in here.
Mm-hmm.
Well, current source is not in this one. Let's look at this one. Oh, here it is. Oh wait, no, that's not the right thing. I want more current source. All right, it occurs 3 times. That's great. That's interesting. So you have a gate-controlled resistor and a voltage-controlled current source. So the voltage-controlled current source is what we just answered, and the gate-controlled resistor is the other scenario. We'll have to find where the other condition for that is. It's in one of these PowerPoints. Question 20. is which of the following is a correct statement on pinch-off condition? So for pinch-off, it's just the electron velocity is higher, and that's the only thing you need to know for the pinch-off region conditions. Everything else is just wrong, obviously. All right, so now it's time to solve some problems. So we'll start with this one. So when it comes to these problems, they're all very similar to the homework, except for this one. I have yet to find the equation for this. I forget what it's asking here. So we'll come to that when we get there. So we'll go through here quickly. So built-in voltage to start. I have some of my old formula sheets here. So built-in voltage, the equation for built-in voltage is, KT over Q, which I just remember is 0.026 times ln of your NA times your ND all over your intrinsic squared. And then that's just the built-in voltage. So for this one, the built-in voltage works out to be 0.84 volts. Does anyone have any issues with doing this particular question, like formula-wise or anything that needs an explanation? Like finding the built-in voltage of a junction given, a couple conditions. All right, cool. So this is something that is.
Could you just go over that? I mean, I know it's a stupid question, but
it's not a stupid question. Yeah, okay, so I can go over. So for this one, it's this one's just a one formula question. The formula for built-in voltage VBI is equal to KT over Q times ln of NA times ND all over NI squared. Those three terms are inside the ln as a parameter, and that's it. So Ni is a given constant. That's, in Ni squared is 10 to the 20th, but Ni itself is 10 to the 10th. Na and Nd in this equation are both 10 to the 17th as given in the problem. And then Kt over Q is just 0.026. That's another constant that's known. So the equation works out to be 0.026 times ln of 10 to the 34th over 10 to the 20th. And when you do the ln of the internal times the external parameter, you just end up with 0.84 volts. And that's it. So that this question to start. So something that you'll see probably in all of these questions, I'm sure, when it comes to these answering ones is, first off, since he's giving partial credit, a very good strategy for this exam is going to be making sure that even if you're not kind of sure on how to do the question, throw some formulas down and start chunking some numbers just in case, because since he's giving partial, it's better to have a shot at getting partial. Well, I'm sure we'll have more than enough time on the exam, so it won't be a time problem. But when it comes to something like this, even if you're 100% certain that you could just go into your calculator and just chunk through the equation and get a number, and you're pretty certain it's right, you should still write it down and write down the equation, plug in your numbers, and then set it equal to and everything and solve. Just in case you're wrong for some reason. It's good to have the
double check. Always write it down just in case you make a mistake. You hit a wrong button, you get a wrong idea. Always write it down so the teacher knows what happened.
Yeah, always write it down. Since we're submitting work here, if you were to, I don't know what his rule on that is, but if you were to submit, let's say you put in the wrong answer on the Canvas and you were to submit correct work. I don't know what his thing is there, but I'm sure you'd get a significant amount of credit, if not full credit. So then question 22, write the value of the depletion width. So this is the total depletion width. It's not asking for the depletion width in one side or the other. And it's in nanometers here. So these types of questions are going to be tricky here because the qualifier he's going to have, because normally if it was just finding the depletion width and you didn't specify a unit, you would just plug and chug and be done with it. But now if he adds a qualifier like micrometers or nanometers, sometimes there has to be a little bit of manipulation there. So the formula for the depletion width is a pretty chunky formula, and it also requires the built-in voltage. So you'll see that stuff that you answered previously is going to come back and be carried through the rest of your work. So it's important you get those early easier ones correct, because if you get them wrong, it'll screw up the rest of your stuff. So WDP is equal to, everything for WDP is under the square root, is equal to the square root of 2 times ESI, which has a numerical value I'll tell later, over Q, times VBI, times 1 over NA plus 1 over ND. And that's the whole equation here. So in this instance, I'll work through this one again just to make sure. So 2 times ESI. ESI is 11.8 times 8.84 times 10 to the negative 14th power. So that's just a number, and that's a constant that's given to you. So that 2 ESI over Q, you can actually, if you wanted to on the formula sheet, which is something I'll probably note on mine when I send it, you can reduce that to a number, as opposed to like doing your work and calculating it every time, which increases the odds of you making an error somewhere with the calculator. You can instead just plug a number in every time. So if I go back up through my work for the ESI, scroll through so much calculator. Here it is. So plugging in all the numbers that we have thus far into this equation and hitting enter will yield you 1.47 times 10 to the negative 5th. Now, you can't enter that as an answer because that's wrong, because it's asking, first off, in nanometers. So there's a couple things we have to do here. The first thing we need to remember is that in this class, our base unit in this class is not the meter, it is the centimeter. So since the base unit in this class is the centimeter, we need to remember that because he's asking for this in nanometers. And if he's asking for it, we need to figure out how to scale it. So the way I figure to scale it is what I do is I take my answer that's in centimeters, scale it back to meters, and then scale it up or down to nanometers. So here, if you have 1.47 times 10 to the negative 5th centimeters, you actually have 1.47 times 10 to the negative 7th meters. Okay, so that's when you convert this to meters. Centimeters is times 10 to the negative 2, convert it up to negative 7. Now you have 1.47 times 10 to the negative 7 meters. And now to convert this to, nanometers, you move the decimal point over to the right twice, and you have 147 times 10 to the negative 9th meters, or 147 nanometers. And that is the answer, 147 nanometers. So in this class, he's done this trick a lot, and I've had troubles with it on the homework, in that units matter a lot, particularly in these types of questions, since the only way to get this question wrong, if you know how to use the formula, is to mess up your unit conversion. And it's definitely going to hit a lot of people. I can guarantee question 22 will probably have 60% of people got it right and 40% will get it wrong. It'll be a trickier question, because when a question seems easy, people get overconfident and they lose their grip on a little tiny thing like a meter conversion or something. Then question 23, estimate the resistivity exactly at the metallurgical junction point. This right here, you'll see this a lot when it comes to PN junction questions. This just means that X equals 0, or right here, right at that dotted line. So that's the metallurgical junction point, X equals 0, whatever you want to call it. So it's asking right there. So the resistivity at that point, when the applied voltage is 0, aka at equilibrium, is at its maximum, well, no, not its maximum point, is at its highest point in the equilibrium system. So this is another formula question. So in this problem, we've been given a couple parameters, one of which is important for resistivity. Hole mobility is a parameter for resistivity. And as you can see, electron and hole mobility are the same here. So that simplifies things. If they're different, you got to make sure to remember to plug them in differently. But the equation for resistivity is equal to 1 over Q times mu n, which is electron mobility, times your n, technically times nx, but you could also say nd at equilibrium because there is no variation in your doping density there. And then plus mu p, which is the hole mobility, times your technically px, but at equilibrium it's just np. All right. No, Na, it's Na, not MP, wacky. All right, so to work this problem out, it's simply 1 over Q. In this instance, you can't leave Q as 1. You have to write it as 1.602 times 10 to the negative 19th times 100, since you can pull this out of the internal because mu n and mu p are both 100. in this question. And then you do times 10 to the 17th times 10 to the 17th plus 10 to the 17th. Oh, wait, no, this is wrong. That's not how you do this question. Sorry. So at the metallurgical junction point, there's a consideration to be made. I almost did that wrong. So here's how this works. There's actually an explanation for it, but I can probably explain it well enough. So how it works is if we go through his like first PowerPoint on PN junctions, there's this right here. This is an important thing to understand. This line is your hole densities or your acceptor doping versus your acceptors versus your donors, or holes versus electrons. And as you can see, as you get across this point exactly at the metallurgical junction point, this is what the whole law of the junction is about. They're equal to each other. And when they're equal to each other, it is simply equal to intrinsic, I believe, which is described here. This is actually him doing it. So let's do it ourselves. So at the junction point, it's considered intrinsic. And the formula for that is actually in one of our homeworks. There's a specific formula for this type of question, and it would be in this homework. Bop, bop, bop. Right here. Here it is. The resistivity at the junction point. You can see that this is the overall equation, which is modified depending on the conditions it's asking it in. But for here, this is the overall equation when taken into consideration and modified using the law of the junction. They get rid of P, X, and X, and they replace it simply with the intrinsic silicon, Ni, because at the junction point, the P and N are equal to each other, which is the condition for intrinsic silicon. So if you do 1/2 times 1.602 times 10 to the -19th power times 100, which is from mu, times 10 to the 10th power, you will get a very, very large number on the order of millions. And it is 2 times 1.602 times 10 to the -19th times 100 times 10 to the 10th power. 1 divided by this yields us 3,121,098. And in the question, it is asked for in kiloohms per centimeter. So we need to reduce this. So instead of 3 million, it is now 3,121 kiloohms per centimeter. 3,121 kiloohms per centimeter at a VA of 0. Now estimate the resistivity in the neutral end side. So this is something that needs to be considered. Now we have to use a different version of the modified equation. So using the law of the junction and this figure, in the neutral end side, the majority carrier, it's actually the same number here as it is in the quiz, is 10 to the 17th. This is a minority, so it's not to be considered. So 10 to the 17th. So in this instance, the modified equation we use is right here, actually. This equation, which is 1/q mu times nd, the majority carrier in the n side. So if you do this, 1/1.602 times 10 to the -19th times 100 times 10 to the 17th power, and you will get 1.602. 1 divided by 1.602 is 0.624. And if you look, it's very, very, very close, if not exactly. And that's because this problem, pretty sure, what do you know? It's 10 to the 17th, literally the same problem, simply with a different mu n. I did 100, right? Yep, all right, well, wacky. Yep, all right, so then that is 0.625 ohms per centimeter. And now question 25, estimate the resistivity exactly at the metallurgical junction point with a new applied voltage. So earlier when it was asking a multiple choice question with regards to whether or not applied voltage affects resistivity, we said that it did. So there is something we have to recalculate here. And what we have to recalculate is actually in this equation somewhere. Nope, down here, right? Nope, it's in here, I think. Right here. So it's asking, yet again, at that junction point, therefore it has to be the intrinsic condition. So this is the equation for this question, essentially, to recalculate your doping densities at that point, because we have an applied voltage. So we can't consider it as intrinsic anymore. We have to consider it as doped to some extent. So instead of intrinsic, you would do 10 to the 10th times e to the 0.5, because that's our applied voltage in this question, divided by 0.52. This equation right here, this little portion I'm highlighting, is all you really need for this portion, for this question, because then you just take your new values of n and p and plug them into this equation right here, and you're done. So in this instance, oh, is there a question? Nope, all right. 10 to the 10th. 10 to the 10th times e, nope, that's not right. 10 to the 10th times e to the 0.5 divided by 0.052 gives 1.5 times 10 to the 14th power times 10 to the 14th power. And then you take this and plug it in to this equation right here. So if you do 1.602 times 10 to the negative 19th times 100 times 1 over, no, that's wrong, times 1.5 times 10 to the 14th times 2 in there, because it's twice since they're identical. 1 divided by this. And the resistivity is actually the same in this question as it is in the quiz question. It's 208 ohms per centimeter. And then estimate the potential in volts at the metallurgical junction point under equilibrium. So this is a question that I got wrong because I didn't understand what it was asking with regards to the sign. So when it's saying estimate the potential in volts at the metallurgical junction point, it's actually a pretty involved question. Where did I do this? What page did I do this on? Probably didn't write it down. That's cool. Well, there's a couple things we need for this. It's asking for voltage at a point. Voltage at a point can be modeled. Voltage V of x is equal to the equation 1/2 times the magnitude of E max, the electric field, the maximum electric field, times the depletion width of the respective side it's referring to. In this case, it's referring to the N side. So it's the depletion width portion in the N side. Now, something that we know about this question that simplifies it a little bit more, because we've calculated a couple things already. We've already calculated the total depletion width, and we've already calculated the built-in voltage, which is intrinsic to this question. You'll see in a second. So something we need to note is the doping densities of both the N type of the N and P side are the same. So this is perfectly symmetrical. So by symmetry, Wn and Wp, which is the depletion width portion of the N type and the P type side respectively, like split up by that, are identical. They're just half of the original depletion width. Normally, if these are different from each other, instead of being identical, you have to calculate the portion. You have to calculate like the fraction that relates each portion, because then one side's going to have more of the depletion width on it than the other, depending on who has the higher doping density. So in this instance, our Wn is just going to be equal to our value of depletion width in half. But here's something that's important to note here. While in question 22, he's asking for the depletion width in meters and nanometers, this is not the number you want to divide by 2. If you use this number, that means you have to scale every other number to meters. And we don't do that. We want to keep it in nanometers. So in this case, you get to take the number that you originally got out of the equation that was to the -5th and use that instead and just divide that by 2. So the original number here was simply 1.47 times 10 to the -5th. So you just divide that by 2 to get your Wn, since they're symmetrical. So you have 1.47 times 10 to the negative fifth divided by 2. Sure, why not? 7.35 times 10 to the negative 6. It's just a number there. Now, the next thing you need is Emax. The formula for Emax, there's a couple formulas, but since we've calculated VBI and the depletion region, instead of using one of the long drawn out formulas, I can use the simple relationship 2 VBI over the total depletion width is equal to the maximum electric field. Therefore, 2 times 0.84, as we calculated earlier, over the original number, which is 1.47 times 10 to the fifth, not the nanometer scaled one. So 1.47 times 10 to the negative fifth for the depletion region. So if you do 2 times 0.84 divided by 1.47 times 10 to the negative fifth, you will get a big number. And then you take that big number, we keep it over. So now the formula that we're working for in order to find the potential at any given point, at this point, the metallurgical junction point, the formula that we're using that I mentioned earlier is 1/2 times the magnitude of Emax times Wn. So we have Wn, we have the magnitude of Emax, and we have 1/2. So now we can simply multiply everything across. So you can take the magnitude of the electric field times 7.35 to the negative 6, which is half of our calculated depletion width, times 1/2, which is 0.5. So it just so happens that this simply works out to be exactly half of our built-in voltage. Why is that? Well, this is a perfectly symmetrical PN junction. Therefore, the voltage is a linear down or up, depending what reference direction we're looking at here. So as of right now, our answer is 0.42. But as I learned in my last attempt, that's wrong. And the reason it's wrong is because if you were to just put in 0.42, that's the wrong direction. Potential needs a direction. So here it's actually negative 0.42. And the reason it's at negative 0.42 is because the N side is at 0 as opposed to the P side, which is at 0. Because let's see, there's a slide where he shows this. Should be under bias. This probably's got it. Nope. Where are you? This one maybe. It's in the homework. We'll just look at it that way. Right here. So this is where he uses that formula. V of X is equal to 1/2 times Emax times whatever depletion width portion we're referencing. In this question, it was referencing the P side, which means the P side is set to equal to 0. So whatever side is equal to 0 is your reference side. So in this instance, you can see that here's your electric field and here's your Emax. So if this side is set to 0, then your voltage goes up this way. So it's positive with P side set to 0 because you expect the flow to go from this to this side. When you look at these, no, it doesn't matter. So if you set this side negative, or if you set this side equal to 0, which is the N side, you would just flip that line on its head. Therefore, it's going to the negative direction because that's just what the graph is. N is set to positive, P is set to negative. So going negative, positive is fine. Going this way means you're going negative. Therefore, since the N side is set to equal 0 here, you have to do negative 0.42 volts. And then lastly, question 27 is, what is the magnitude of current in nanoamps through the diode when VA is equal to negative 1 volt? So there's a really easy formula for this. It is J, and it actually calculates current. So here's something that's a little wacky. So he's asking, what is the magnitude of current in nanoamps through the diode, right? But what he's really asking is, what is the magnitude of the current density? Because that's everything we refer here is with regards to centimeters squared or something. We're not asking about the total current through the system. We're asking with respect to like a certain area, which is why it's the current density. So the formula here is J is equal to that I0, J0, whatever you want to call it. That's an intrinsic given. So in this instance, it'll be 10 times E to the VA over 0.026 minus 1. So it's e to the VA over 0.026, done, minus 1, all in parentheses, multiplied by 10 nanoamps. So VA is given as -1. So what happens when we do that? Well, a relatively large negative number as the power of E is going to essentially give us 0. For all intents, it's to the -17th. It's just a super small number. And then that super small number is being subtracted by 1. So it's essentially just going to give you the whole internal parameter of this equation is just going to spit out -1. So you're going to have J is equal to 10 nanoamps times -1, which I'm sure you all know just means you have -10 nanoamps.
This is good stuff.
Yeah.
Mm-hmm.
But now here's the thing. We have -10 nanoamps, which is what I put into my answer. And it was wrong because the question asked about the magnitude. So this question, you could do this question without any math if you knew the principles of the PN junction and how this works. VA is negative. If VA is negative, that means you can assume the system's operating in reverse bias. When a system's operating in full reverse bias, which is determined by the applied voltage, because you can operate in a very slight region of like reverse bias where there's just a little bit of current flowing properly. And you can know that because, or, you know, a little bit of current, it'll always be negative simply because it'll always have a negative sign on top, but it'll just be a little bit bigger. But in this instance, it's way too big, you know, because -1 divided by 0.026 spits out a rather large negative number. So the E evaluates to essentially 0. And whenever you have a negative voltage, the system's simply going to be some negative multiple of 10, or some negative multiple of your J0 or your I0, whatever is given to you at a time, because it can either be J, I. So when you're operating in reverse bias, the answer is just the negative of this, but if it's asking for the magnitude, the answer is just I0, which is 10. And it tells you in nanoamps, but that's just given. All right, time to figure out how to do these questions. I haven't gotten to work these yet, so we'll be learning together. All right. Consider an ideal N-channel MOSFET with P-type substrate having a doping density of 10 to the 17th. We have the given parameter of oxide thickness. We have a channel length, channel width, and an electron mobility of 100. And these are our dielectric constants. So here, I told you earlier that the ESI is 11.8 times epsilon 0, but in here I used 11.9. And he also says epsilon 0 is 8.5 instead of 8.4, so whatever you want. Yeah, 8.84 and 8.85. I just use the ones that I memorized just because. So let's look through these questions. All right, first question here is, what is the value of oxide capacitance in the units of microfarad per centimeter squared? So the thing is, when it comes to MOSFET, I don't believe we had too many, let's look at the homework. So this is the last homework that we did, and it was all about MOS capacitor. So we've really never done an assignment that had to really utilize some of these questions or some of these values. Like if we go back to the quiz, like I don't believe I've ever done a question that required me to use L and W. Does anyone else remember having to use these parameters, like channel length and channel width?
I don't. Outside this quiz, of course.
Yeah, I don't remember if I ever had to use them. Like here, because like I know these formulas, but we've never had to use it. So this is going to be interesting. So here's where we start on MOSFET. I have a bunch of information. Oh, why is this searching? Get out of here. We have inversion characteristics of MOSFET. Here's some formulas. Oxide capacitance. Looks like we found what that might be. Cox. So now we have to find where Cox is defined. I think it's defined over here somewhere. Here's it here. It appears again. I put it somewhere. I think. All right, I think I know it. I think COX, the formula for COX, or what is it determined as here? Oxide capacitance. I'm pretty sure the formula is COX is equal to epsilon OX over TOX, which are both given parameters. So understandable why the first question is something that's just a constant divided by a constant. So here our epsilon OX is defined as 3.9 times epsilon 0. So we would just do 3.9 times 8.8 for this question, 8.5 times 10 to the negative 14th. Divided by TOX, which is given as 2 nanometers. So given as 2 nanometers, but remember that for the most part, everything we're working with is in centimeters. So numerically, 2 nanometers is written as 2 times 10 to the negative 7th. We're just taught to scale to meters, but when we're working these problems, unless specifically told like previously to scale, where you'd have, in order to solve it, you'd have to scale it to meters. In this instance, this is assumed to be scaled to centimeters. As you can see, our doping density is in terms of centimeters. Therefore, we have to work in the centimeters. So it's a bit tricky there because giving you an oxide thickness of 2 nanometers, a lot of people are inclined to write 2 times 10 to the negative 9th, and that would make their answer wrong. So you can't be doing that. You got to write it in terms of centimeters. So if we do turn my calculator on, 3.9 times 8.85 times 10 to the negative 14th divided by 2 times 10 to the negative 7th power. And you will have 1.725 times 10 to the negative 6 farads per centimeter squared. But here's something, it says microfarads per centimeter squared. So can we scale that? Can we just say this is the answer? Let's find out. Pretty sure that we did answer a question with regards to oxide capacitance in this homework somewhere. Voltage drop, electric field. What is the operation of the Mos capacitor? Charge, 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 charge. We really never calculated this, did we? We really never had to do this. That's wacky. That's funny. All right, let's go back to this one then. No, this one. Pinch-off square law. All right, so we have a number. It's 1.75 times 2. Yeah, 1.725 times 10 to the negative 6th. Now, that's scaled to centimeters. So, technically, so it's already scaled to centimeters, and it's to the negative 6th, which is a different parameter, and it's in for farads. So theoretically, we could just enter 1.725 here. So I'm not entirely sure on this one. I'm sure we'll find out in a second once we're finished here and submit whether or not that was the correct unit scaling. So I'm pretty sure the formula is correct. It's just a matter of figuring out how to scale properly to the microfarad, because as you can see here, he emphasized that micro, which is a bit tricky. Who knows? Value of the threshold voltage of the Mosfet. That is just another formula. We talked about it earlier. And this is there's no applied voltage here, so that's cool. So VT is simply going to be equal to voltage in the oxide plus the Cool's fork looking thing. I don't actually remember how to say that one. Let's see. I'm talking about where are you hiding from me? Yeah, anyone remember how to pronounce this?
Is that what you're?
Does anyone remember how to? I mean, it's called surface potential, but We'll just say it. We'll just keep it with that. I don't need to
Oh,
speak.
psi. That's going to be like yeah.
All right, yeah. I really don't. I'll just call it surface potential then. All right. So the formula for threshold voltage is voltage in oxide plus the surface potential. So both the voltage in oxide and surface potential have their own formulas to solve for them. So voltage in oxide is going to be equal to Q times Na times the T oxide over epsilon oxide times WD, which is depletion, and then surface potential is going to be equal to Q Na over 2 times epsilon Si all times WD squared. So everything that we need is given except for WD squared, or WD at the moment. We don't know the depletion width, so we have to calculate that. So this is something that I've always wondered what the proper way to do is, because we have to do this all the time. Because when you look at these things, the first question is almost always find the threshold voltage. And threshold voltage for the MOS capacitor and the MOSFET are identical. I believe the formulas don't change. So let's look. Surface potential. Oh, here it is. You can solve for surface potential first using this formula. And then you use the surface potential formula to find the depletion width, which is reorganized like this. Yeah, so this question right here from the homework is identical to what we're about to do, essentially. This process, I mean. So the first step is to calculate the surface potential using that formula there. So it is going to be 2 times 0.026 times ln of Na over Ni. Na in this instance is 10 to the 17th, awesome. So we have 10 to the 17th divided by 10 to the 10th, yay. And that gives us surface potential of, who would have guessed, 0.84. Okay, take that and you plug it into this next equation in order to rearrange it and solve for WD, since we need WD to solve for the voltage in the oxide. So if we do 2 times ESI, which is going to be 11.9 times 8.85 times 10 to the negative 14th, times your surface potential, which is 0.84, all divided by 1.602 times 10 to the negative 19th times 10 to the 17th. Take that, divide it by this. That's not what I want to do. And then take the square root of that. Yeet. All right, so the WD has been calculated, and WD for our question on this quiz is 1.05 times 10 to the negative 5th power. Take that and you run it through the V oxide equation. So you'll do 1.602 times 10 to the negative 19th times 10 to the 17th times T oxide, which, as we wrote earlier, is 2 times 10 to the negative 7th here. And then yet again times the new number, which is 1.05 times 10 to the negative 5th, which is our WD, all over epsilon of oxide, which was 3.9. Oh wait, I'm gonna write this right. 3.9 times 8.85 times 10 to the negative 14th. Take this, divide it by this. Okay, so our threshold voltage is super tiny, which is what you should expect. If your surface potential is lower than your threshold, there might be an issue. So the threshold voltage is also very similar to the one that we see. Oh yeah, your threshold, your oxide voltage is lower here, and it's 0.097 for our question. So if you do 0.84 plus this, you will get 0.937, which I will round up to 0.934 for our purposes here. Wait, no, I'm at 9.4. Yeah. What is the voltage drop in the oxide when the gate voltage is equal to 5 volts? Assume all terminals are grounded. Wacky. All right, let's go back to this then and look at it, because we've done all of these again in his formulas before. I'm almost certain of it. Not this one. Should be up here probably. Let's see. What's the question here? Voltage drop in the oxide when the gate voltage is equal to 5. That seems an awfully like. Find the voltage drop in the oxide when the voltage is equal to 0.5. But here he just upped it to a kind of a ridiculous amount. So if we go down to part G, voltage drop in the silicon and then the voltage drop in the oxide is calculated using this. So the change here looks like a change in WD. Because here's what he does this first. All right, cool. So this is something that needs to be noted for solving these types of questions, because in this quiz, he doesn't ask like in the homework, he asks the questions really regimented because each question builds onto the next one and almost always the answers carry through. But this time he left out the question before this, which is recalculating your WD, which would leave you to assume that it's just the same, which is obviously wrong. You know, the drop in the oxide is not going to be the same amount, because remember I said when there's a voltage drop across a MOS capacitor or MOSFET, the majority of the voltage drops through the oxide. And in the previous question, the oxide only dropped the voltage by 0.097, which is far less than 0.84 of the surface potential. So that's a problem. We need that to be a lot higher. So when we go through here, our first step in solving a question like this is recalculating this, which is recalculated by rescaling his WD. So how did he rescale his WD? Right here. Oh boy. He used his quadratic. But why? So right here he says we are under a depletion regime. And this is for 0.5 volts. Depletion regime is when it's in the off state. So obviously it wasn't enough to start it. And we know that because the threshold voltage of this system was 0.9 volts. He didn't even reach it, therefore it's still in the off condition. So you basically lose almost all of it immediately. So we are probably in the inverted regime. So we need to find the equation for inversion. Let's see. Does anyone remember the inversion regime equation? Let's see. It might be the same, who knows? No, here is where it starts. Did it show up anywhere? That's cool. Luckily for me, I can just type inversion across the board here. So this is the governing equation in depletion. So that's what it said. We're in the depletion regime, and this was its governing equation. Does it not use that equation? That's interesting. No, we know about this equation already. This is important to know because this is definitely a question that's going to get asked. It was asked on the homework and it's being asked here. So this means we're in inversion since we're obviously in the on state, since we're past the threshold voltage and everything's grounded. The voltage drop in the oxide yeah, so this was because he was under depletion regime, so he got to recalculate using the quadratic solution in order to find WD. But I don't think we get to do that here because we're not under the depletion regime as stated, like up here somewhere. We're at the onset of inversion, which means we're under this. Well, what modifies there? That's not right. Because we just calculated this Vox, there's nothing there. The only thing that should change here is the depletion region. I'm not sure what scales up differently. Anybody have any ideas on this one? We haven't done a question like this where it's at 5 volts, I don't believe. Let's see, maybe we have. Here, let's look at I. I says voltage drop of 2 volts, that's past the threshold, so this should probably have the answer for us. Yeah, beyond inversion. Oh. Well, that was easy. Okay. All right, everyone remember this, because I just spent probably 5 minutes sitting here like a dummy when the answer was super simple. When you're beyond inversion, you simply take the voltage that is applied in order to find oxide voltage, the drop across the oxide, the voltage that is applied, and then you subtract the surface potential. The surface potential, which is the same because it's beyond inversion, so it has the same condition as we calculated previously. So our surface potential is still 0.84. So our voltage drop in oxide is going to be 5 minus 0.84, boop, 4.16. Who'd have thunk it? And if you guys remember, there were questions, multiple choice questions for quiz 4, I believe. Mosfet, yeah, quiz 4 that were exactly like this, where it would ask, it would be a multiple choice question instead of a calculation question. And it would say, you know, how much of the voltage drops in the oxide if the applied voltage or the gate voltage is equal to like 5 volts. That was exactly the question. And then it had 4 options, and the correct option was a little bit more than 4 volts. And what do you know? It's 4.16. All right. Question 31. What is the value of inversion charge density in the channel when gate voltage is equal to 5 volts? So this is a channel. So this is what it's asking. And we're expressing this in microcoulombs per centimeter squared. So first off, we can look here, and this looks like the right thing. But it said inversion charge density in the channel. So yeah, it's the same unit. So let's go up and make sure. Charge on the gate. It's part J. Note after inversion is much higher than the charge during depletion. Well, obviously. All right, so this is the formula for here. Let's go back to this real quick. What is the value of inversion charge density in the channel when the gate voltage is equal to 5 volts? So this is exactly what is given here. So the formula is QG is equal to C oxide times V oxide is equal to this. So we know what the V oxide is. We just calculated it in the previous question. It's 4.16. And we also have calculated COX previously, which was, I don't remember that. It was small. I'll just go back up in the quiz and look at it when we need to. So we just go bop, 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 bop. So it was going to be 1.725 times 10 to the negative 6th times 4.16, because that's the voltage drop in oxide. Bop, we have a number. So let's confirm. So this says 2 microcoulombs per centimeter squared, and this is at 2 volts. So for us, we're looking at 7.2, or specifically 7.17 microcoulombs. So that's to be expected. It's super close to the previous one, but that was at 2 volts and this is at 5 volts. So obviously greater voltage is going to have a greater charge density. Hopefully that's right. This being incorrect doesn't mean that this process for this question was wrong. Most likely it means that our assumption here that this is already scaled to the proper units was wrong, which is something I've been thinking about. But we'll find out, obviously. Question 32, what is the magnitude of the on current in milliamps for this MOSFET when gate voltage is equal to drain voltage is equal to 5 volts? So let's see if we've done this before. Probably have. Current would probably be in the second question. Electric field. Looks like we might not have done current. Let's go back up here one more time. If not, then I'll consult my formula sheet. Oh, cool. All right. Magnitude of on current milliamps. Let's see if I listed down a current equation here. If not, I'll have to go to the PowerPoints to find his current equations. All right. PowerPoint time, gangstars. Ooh. Pop. Yeah, this is the intro slide anyway. Let's go here and look for current. Nothing about current here. Cool. Nothing about current there either. All right. It's getting towards the last PowerPoint. How many people have attended every single lecture? If anyone. Let's see. Just starting to find current. All right. This is definitely, this has to be it. This has to be it. 100% this has to be it. What's VDS? That's the drain. Low VDS, it's like grounded, I think. So this is probably the linear regime we're looking at, although no, because that can't be it. Let's look at this question one more time. Okay, no, it gave it to us. It gave it to us, and it was in this formula, this one. Bro, what? I think it was right here. Yeah, it's this one. So VDS is equal to 5, but the question is that okay? Because this is what I'm concerned about. These regions, because all of these have different governing equations. So now I can see where the width and length of the channel come in. Obviously, it's for calculating current, because this is the only formula that's used it thus far. So this is definitely going to be something I'll have to detail on the formula sheet. But the question is, which one of these governing formulas we can use for this question? So this is saying MOSFET, linear regime, low VDS. VDS referring to the voltage on the drain, which is in this question, given to us as 5 volts. So this is the same as the gate, but then this next question is asking the same question, but with a drain voltage of 0.5. And I'm inclined to believe that that means that this is the formula we use for the next question, because it says low VDS. Channel pinch off at high VDS. How's current flow if there's no charge? So this, whatever, I think this is what we're looking for. This equation for this question. So this is the equation we'll be using for this question. Beautiful. So our current is equal to, I'm going to move the quiz over to the other thing so I can still see. Let's see this one. So the numbers we're working with here, so we need a couple things. So W was equal to 1 micrometer. So since we're working in centimeters, that means W is 1 times 10 to the negative 4th over 2L, which is also 1 micrometer. So that means 2 times 10 to the negative 4th power, all times mu F or mu EEF, which in this instance is a given as electron mobility. So that's just times 100, which is given in our problem. And then C just to recap, when we're considering room temperature, that's 300 Kelvin, right? That's what that KT over Q is. It's 300 Kelvin.
Mm-hmm.
Okay, good. Because I just looked at this question, and the last line said answer the following questions assuming T equals 300 Kelvin, and normally it would say room temp. So I got a little scared there for a second because that would ruin every single answer we have. because everything's dependent on that little relationship. And then our next portion is, so this is a given, these are given. So this whole first portion is given here. And then now we're looking at Cox, which we calculated previously. And we hope that it's correct, is 1.725 times 10 to the negative 6. And then the last thing is VGS minus VT. So for our question, VGS is gate voltage is equal to drain voltage is equal to 5 things. So the voltage, the threshold voltage is, we know. The threshold voltage we calculated previously is 0.94. The gate voltage that was given in the problem is 5. So it's 5 minus 0.94. Beautiful. Squared. That is squared. All right, let's run through and calculate here and see what type of answer we're looking for on the order of. It says that it's asking for answers on the order of milliamps. So let us hope that is what this spits out, shall we? It's 100 times 1.725 times 10 to the negative 6th. 5 minus 0.94 squared. One, two, three. This spit out 1.4 milliamps. Sounds about right. All right, 1.4. Beautiful. All right. Now this one, remember when I just did a bunch of thinking? And by the way, this is the first time I've ever seen this since we've never had to do this before. And I did not attend this lecture. Square law. The reason I assumed that this is what we're using for question 32, I'm going to move this. Actually, I'm going to open the test again. The reason I assumed that we're using that equation for question 32 as opposed to the other equation is because here the voltage on the gate was equal to the drain voltage, which is 5 volts. Now, to me, that seems a little ridiculous. That seems like a high voltage. And the reason I was tricked about that and realized that this was something that we need to look at was because later it says 5 volts on the gate and the drain is 0.5 volts. Therefore, I was able to deduce that a low VDS regime, this is the equation we'll use for the next question that we're about to do. So that's the equation we're working with. Constants across the board. We still have 1 times 10 to the negative 4th for our width, but now it's just 1 times 10 to the negative 4th for our length. Therefore, that's just equal to 1. Cool, that gets out of there. Now we still have 100 for that mu. Then we still have the same oxide we calculated previously, which is going to be 1.725 times 10 to the negative 6th power. Just confirm that real quick. Yeah, that's what I wrote last time. And then times the gate minus threshold, which is still the same. So 5 minus 0.94. But as opposed to squaring this parameter, now we multiply it by 0.5 volts, which is our given drain voltage for question 33. So let's hit it. So 100 times 1.725 to the negative 6th. 5 minus 0.94 times 0.5. I take this times this, and this spits out 3.5 times 10 to the negative 4th power, which means 0.35 milliamps if I were to scale that up to milliamps. And the last thing is asking, what is the magnitude of drain current in milliamps in this MOSFET when gate voltage is equal to 0.05 and drain voltage is equal to 0.05? Now this is interesting. This is a new condition that we haven't considered. So this is the first time we see these regime current questions. So this is for low VDS. So I'm intrigued and I believe I might want to use low VDS here. But then we go up here at high VDS. That's the pinch off. That's where that comes into play. This is not what we're going to use here because VDS is obviously small. And this is beyond pinch off. Yeah, it doesn't matter. So I'm pretty sure we're still using this equation right here. It's just going to be negative, but not negative because it's asking for the magnitude. Don't make that mistake. I make that mistake. It's a dumb mistake. So we will do 100 times 1.725 times 0.5 minus 0.94 all times 0.5. So let's run that through and see what it spits out. We have 6. And then we do 0.5 minus 0.94, up, take that, multiply it, beautiful, times 0.5 again. And I have something to negative fifth, and it's a super small negative number, but we'll change the negative out of the way and say 0.038 milliamps, since it's asking for the magnitude. Okay, let's see if I'm right on these last couple questions. I'm very interested to see how my answers are like, or our answers are like in this MOSFET, because historically I perform worse on MOSFET than I perform on other stuff. So let's see.
Okay.
I got a 90. Cool. All right. Let's go through, confirm everything. So I was able to correctly answer all of these. Therefore, my explanations were hopefully satisfactory to anyone watching and anyone to be watching in the future for all the multiple choice questions across the board. Don't just study these for the final, because he's obviously, a couple of them show up again because he's done so in the past, but honestly, it'd probably be in our best interest to go back and look at some of our old quizzes if they're available. If not available, to look over again. I'm pretty sure there's been someone who's been making Quizlets of these questions, a couple of them. At minimum, I know the PN Junction quiz has a Quizlet available for these questions to look over. I don't know about the MOSFET one. I'll ask him to send a link again in the chat. So all of these were correct. Now we go to the PN Junction, everything on the PN Junction is 100% correct. All the explanations and formulas I used and methods I told you is exactly how you want to solve these questions. So keep that in mind. Now let's look here. This is what I'm interested in. Okay, our assumption was correct here, which is great. So you don't need to do unit scaling for oxide capacitance. Threshold voltage is a formula. Voltage drop in the oxide is a formula. Here's some, oof, what happened here? I was close, so it's probably a calculation error on my part. Sorry about that, but I'm sure that the method is sound. And then last year, it was just 0.
Hey, Ethan, can you hear me?
Yeah, what's up?
No, I actually remember this one. I know what's going on here. The reason it's 0 is because we're not in forward bias. We're not conducting anything. The gate voltage is still under the threshold voltage, so nothing's conducting. It zeroes out.
Yeah, makes sense. I probably should have seen that. Yeah, so anyone watching in the future or watching now, explanation for question 34 as to why it's incorrect is because, as Jack just said, it zeroes out because the gate voltage is still far lower than the threshold voltage, therefore nothing is flowing. No current's conducting. And then this one was probably correct. I probably just did a calculation rounding error somewhere, considering it's super close. That's on my part. That's my bad, sorry. All right. That is that for this one. I finished 2 minutes before my scheduled calculus review session. Awesome. And it took 79 minutes. Beautiful. So I know that we have more time to take this final than that, I think. So, you know, if you're taking the final and you're not sitting around explaining every question, you should be fine on time. So that's great. I will put together. I'll put together a formula sheet and I will send that out before the exam. Sam, are you trying to say something? You're like muting and going in and out. You're like lagging or something.
You are going to post this video on YouTube, right?
Oh yeah, of course, every time. I'll start rendering that as I do the other one, and that shouldn't be a problem. Yeah. All right, and I'll make a formula sheet for this and I'll post it in the group me before the exam. Our exam is the 10th. I made sure to confirm that, right? It's the 10th. Everyone agrees? Awesome. If it's on the 10th, that means I have a couple days. I'll try and get it out tomorrow.
Yes, it is.
If I don't get it out tomorrow, it'll definitely be out by Tuesday night. So it'll still be out a day or two beforehand. When I post it, I'll ask everyone else to check over my work because I'm not omniscient. I don't know if I have all the formulas or if the formulas are right. So that'll be more of a group effort, not just me putting stuff together. So make sure to look ahead for that. I finally get to close 1,000,000 tabs. That's great. And I will end this and post the video. Who's chatting? Was someone chatting? Oh, that was great. That was Grady. All right, cool. All right. Thank you everyone for attending, and hopefully we all do well on this final. Time to get this semester over with.
Very much so.
Agreed. All
But
right.
thank you. This has been awesome as always.
No problem. This helps me. This is my way of studying because when I put myself on the spot forcibly and have to explain something, I'll tend to remember it for the rest of my life, either out of sheer embarrassment or awe of my own ability to just go off. All right, time to go. Good luck, everybody.
Mm-hmm.
Alrighty.
Yeah.
See ya.